Welcome to our exploration of one-dimensional kinematics, where we'll delve into motion along a straight line. This lesson is tailored for algebra-based physics students, specifically those in Physics 301. This lesson is prepared by Dr. Moses and Tom, Associate Professor of Physics. I'm Dr. and Tom's virtual teaching assistant. By the end of this lesson, you'll be equipped to distinguish between scalar and vector quantities, define key motion concepts, apply kinematic equations, use problem-solving methodologies, and interpret motion graphs. Kinematics is the study of motion without considering forces. In one-dimensional motion, we focus on movement along a straight line, analyzing the relationships between position, velocity, and acceleration. This forms the foundation for understanding more complex motion, using algebraic methods. Motion is always relative to a reference frame. By choosing an origin and establishing directions, we can consistently describe motion. For example, on a highway, we might use mile markers to define positions and directions. Position describes the location of an object relative to an origin. It has both magnitude and direction, and can be positive or negative. For instance, a position of plus 15 meters indicates 15 meters to the right of the origin. Displacement is the change in position, not the total distance traveled. It's a vector quantity, meaning it has both magnitude and direction. For example, moving from 2 meters to 8 meters results in a displacement of plus 6 meters. Average velocity is calculated by dividing displacement by the time interval. It's a vector quantity, indicating both speed and direction. For instance, a car traveling 100 meters east in 20 seconds has an average velocity of 5 meters per second east. Instantaneous velocity is the speed at a specific moment, like what a speedometer shows. It tells us both speed and direction, and is represented graphically as the slope of a tangent to the position curve. Average acceleration is the change in velocity over time. It's a vector quantity, and graphically, it's the slope of the velocity time graph. For example, a car accelerating from 10 to 25 meters per second in 5 seconds has an average acceleration of 3 meters per second squared. Instantaneous acceleration is the acceleration at a specific instant, like the jolt you feel when braking. It's the slope of the tangent to the velocity time curve and is crucial for understanding sudden changes in motion. Scalar quantities have only magnitude, while vector quantities have both magnitude and direction. For example, distance is scalar, while displacement is vector. Understanding these differences is key to solving motion problems. Let's look at an example. A car travels 100 meters east, then 60 meters west in 80 seconds. Scalar analysis gives us total distance and average speed, while vector analysis provides net displacement and average velocity. Here's a summary of key mathematical definitions: displacement, average velocity, and average acceleration. Remember, delta indicates a change in a quantity, which is fundamental in kinematics. Kinematic equations for constant acceleration link velocity, position, and time. Equation 1 relates velocity and time, while equation 2 connects position and time, showing a quadratic relationship. Continuing with kinematic equations, equation 3 links velocities and displacement, while equation 4 uses average velocity. These equations are essential tools for solving motion problems. To select the right equation, count known variables, identify unknowns, and ensure the equation fits the situation. You need at least 3 knowns to solve for one unknown, following a strategic approach. Special cases in kinematics include free fall and constant velocity scenarios. Understanding these cases helps in applying the right equations and concepts to real-world situations. Our 6-step problem-solving methodology guides you through analyzing, drawing, listing, selecting, solving, and checking. This structured approach ensures thorough and accurate solutions. When drawing diagrams, use a consistent coordinate system, mark initial and final positions, and clearly label directions. These tips help visualize and solve motion problems effectively. For variables and units, list all given information, identify the target unknown, and ensure you have at least 3 knowns. This clarity is crucial for solving kinematic problems accurately. When tackling problem solving, the first step is to match the knowns to the equation variables. This helps in selecting the right equation to use. If time is unknown, equation 3 is your go-to. For position or displacement problems, consider using equations 2 or 4. The decision matrix is a powerful tool for selecting the best equation based on known and unknown variables. By identifying what you know and what you need to find, you can choose the most suitable equation to solve the problem efficiently. Before finalizing your solution, it's crucial to perform some final checks. Ensure the units are correct, the magnitude is reasonable, and the sign makes physical sense. These checks help verify the accuracy and reliability of your solution. Let's dive into an example of constant acceleration from rest. Imagine a car accelerating at 2.5 meters per second, squared for 8 seconds. We need to find out how far it travels. By using the appropriate equation, we calculate the distance to be 80 meters, which is reasonable for the given time. In this example, we explore the maximum height reached by a ball thrown upward at 15 meters per second. By applying the correct equation, we find the maximum height to be 11.5 meters. This demonstrates the importance of using the right formula for accurate results. Continuing with the ball example, we now calculate the time it takes to reach maximum height. Using the equation for time, we determine it takes approximately 1.53 seconds. Verification confirms the accuracy of our calculations, ensuring the solution is sound. Next, we examine a car braking from 25 meters per second to a stop in 5 seconds. Our task is to find the braking distance. By applying the relevant equation, we calculate the distance to be 62.5 meters. Additionally, we find the acceleration to be -5 meters per second squared, indicating deceleration. Kinematic graphs are essential for understanding motion. The slope of a position time graph represents velocity, while the slope of a velocity time graph indicates acceleration. The area under a velocity time graph corresponds to displacement. These principles help visualize and analyze motion effectively. To summarize one-dimensional kinematics, we focus on key concepts such as position versus displacement, velocity versus speed, and acceleration. Motion is always relative to a reference frame. Essential equations and a 6-step problem-solving methodology guide us through these concepts, preparing us for the next topic: two-dimensional motion and dynamics.